Let me first introduce Daniel Rohr. You, as I learned a few minutes ago, are chemistry scientist by education, and you're active in the machine learning and data science domain for quite some years, and in the programming scene. You are tackling a topic today that has a big importance for society today, but without going too much into details. The topic is about CO2 savings with machine learning in transportation traffic. I'm very looking forward to your talk. As I said, if there are any questions from the audience, please go ahead, ask them right away. I'm super happy that you're here, Daniel, and that should be it. The stage is yours.
Okay, cool. Well, thanks a lot also for the invitation and for the introduction. I'm happy to speak about what we're doing at TRAX. And I have a slide that introduces me again. I'm sorry. So I studied chemistry, and then I got a PhD in what's called quantum chemistry. And maybe also for your understanding, that's a bit an intersection of physics and chemistry. So it is about the simulation of matter on an atomic or molecular scale. And I was doing around about 10 years in fundamental research, where I tried to describe, or accurately, we have to say very accurately, tried to describe bond making and bond breaking processes, which are basically at the core of chemistry, right? Chemistry is all about making and breaking bonds. And I was active there developing models. About 3 years ago, I decided to go into AI. And that's also where I kind of met Miguel in one of these many, how they call it, a data science retreat. Boot camps, right? You call them boot camps. And now it's almost 2 years by now that I am with TRAX, and I will talk about what we do at TRAX. But also just for your understanding, we are an AI company, almost 4 years old now. We have about 17 employees. Our headquarters is in Berlin, in Germany, of course. And so we are looking at trucks and how they move on the street, and try to improve a bit on their fuel consumption, basically. And this all goes into the CO2 emissions, as you probably know. This is an overview slide for companies that want to or need to report CO2 emissions, and it's a rather complex topic, because if you look at the whole company, there are many different contributors to your CO2 emissions. And one thing is called the scope 1, that is direct emissions. So let's say if you burn something, right, then you emit CO2. The scope 2 is exclusively electricity, and scope 3, and that's what we are in, is what they call the indirect. So that is everything with transport, basically, right? We have here this little icon here, the freight transport. And depending a bit on which industry you're looking at, then the percentage of CO2 emissions of a company that is in the freight, in the transport, is somewhere between 90% for, let's say, fashion industry, down to maybe 30% for typical nutrition food industry. In the food industry, you have a lot of CO2 in the production, in particular if you're into food that involves animals, right? Animals are very CO2 heavy. So we offer our customers a carbon accounting tool to accurately calculate their emissions from the freight, from the transports. So we offer that both to we call them carriers. So those are companies that have trucks, but also their customers. But this is not what I'm going to talk about. But I wanted to just let you know also what TRAX is about. And here's the mission statement. We say, okay, to accelerate the transition to a carbon-free freight transport industry. And then it says through efficiency. And this is basically how my journey started at TRAX. It was actually in the job interview that our CEO, the founder, Jacob, he was talking about this, and he was talking about efficiency. And he said, well, see, you know, these trucks, they go on the road, and you have a driver, and the driver drives from A to B and consumes, let's say, 100 liters of diesel. And what we want to offer is a tool that describes their efficiency. Because going from A to B, maybe you could have done it with 90 liters or 80, or maybe 100 was already perfect. So we want to be able to, to calculate or measure efficiency. And then I was thinking after this interview, I thought, like, yeah, okay, you know, I understand why you want to do it, but I was thinking, okay, how can you measure efficiency of a truck, right? That's really difficult. How do you do that? And we came up with I thought a very, very neat idea how we do that. And for that, first of all, we forget any boundaries. We have no time constraints, no money constraints, no space constraints, and we have our thought experiment. And this is how our thought experiment looks like. We take a trip that we are interested in from A to B. So let's say from Berlin to Munich. And we consume, let's say, 100 liters of diesel. And then we rewind time, okay? We go back in time to the exact same point in time, and we take a different truck, and we go with that different truck and maybe also the different driver on the same route under the same conditions, okay? And then we rewind time again, and we take the next truck, and we repeat this, and we do it again and again and again. And then we can compare all these fuel consumptions of all these different trucks. And that is then our measure of efficiency, basically. So our answer to what is efficiency, we say, first of all, it is relative, right? Efficiency can only be relative to something else. And here's now just an example, okay? We say my truck had a consumption of 100 liters, and the other truck, let's say 110, 108, 112, and 99 liters. So when I look at this table, I would say, well, I was pretty efficient, right? And please tell me that you disagree if you disagree with me, but I think if you consume 100 liters and 3 other trucks consume more, considerably more, and 1 other truck just 1 liter less, so 1% less, I believe that was pretty efficient. And this is our basic idea behind it. Okay, this is how we think and how we operate here most of the time with almost all of our questions that we are looking at these business questions. This is the foundation. And you notice that I haven't talked about AI at all, but I guess that you already figure out that obviously we cannot rewind time, and how can we have other trucks under the same conditions while we use AI? And I will talk about that a bit more. But what is really interesting then, if you do that, is you get many trucks, and you have a normal distribution, and you can locate your own truck on this curve, on this, I'm sure you all know this, it's a famous Gaussian. And so if my truck was located here, right, I would say the truck was very efficient. Remember, lower is better here, right? Less fuel consumption is better. So that's why this green dot means I was very efficient. If my truck consumption was here, I was kind of mediocre. And if I'm here, I was rather inefficient, right? Because many other trucks were on the same trip, and they consumed less than my truck. This is how we think about it and how we can analyze the efficiency of our truck. But that's just one. That's the beginning of many business questions that you can ask. And so if you think about this, here's the timeline. We are here today. Then we can look in the past, which we will call descriptive, right? What has happened, and we can analyze that. But we can go and become prescriptive, and we say what could happen in the future in order to make a decision. And then even what should happen, right? We optimize it in order to then execute it. And this is the way that we basically try to save CO2, is by optimization, by just trying to find whatever parameters, and I will talk about this a bit, to optimize your operations. If you're a fleet manager, right? So you think of yourself as somebody who's operating, I don't know, 10, 100,000 trucks. This is our basic idea. All right. Now, what do we do? Current trucks, let's say if they're built within the last 5 years, they come with sensors already included. All right. And these sensors, they record a number of different fields. And I put them down here on the left. You see different types of speeds, even the pedal position of your gas pedal, right? Which gear, GPS, very easy, right? Weight, trailer, driver, whatever. They also record the fuel consumption. We see that as well. And this data is collected while they're on the road, while they're driving. Whenever you see a truck on anywhere in the city, on the Autobahn, anywhere, they're collecting this data and they're transmitting this data into the cloud somewhere between every 30 seconds or every 5 minutes, somewhere in between that range. And that data is stored in the cloud and is made available for services just around these fleet management problems. One of them is, you can easily imagine, something that they call track and trace, right? So they have a big map where they see all of their trucks and they see their destinations and they see an estimated time of arrival. And this is something that you get out of this data, for example. That is one service. But obviously, it's also the data that we use in order to do our models. So we take the parameters on the left, and we have already automatically basically a label, the fuel consumption, right? And we have that not for a whole trip, but we have that for small little pieces, for segments, or we like to call them snippets, right? So a truck is on the road for, let's say, 4 hours, and the whole tour for 4 hours is decomposed into many little snippets. Each of the snippets cover a segment of somewhere between 30 seconds and 5 minutes. So you see that the whole distance, the whole trip can be decomposed in many smaller snippets. And now they go every day and every week and every month and every year and for every truck. So we got lots of data and continuously get lots of data. Okay. And since the fuel consumption is just a number, right? And it's a number somewhere between 0 and, let's say, maybe 5 liters. They usually don't consume more than 5 liters on these small little segments. We have a regression problem, basically. And it's well known regression problems are good problems for data scientists. Well, we know how to solve them, basically. That's why I write down here your favorite ML model, right? Okay, so the favorite ML model starts obviously with a random forest, but it doesn't end there. And I guess you're familiar with neural nets. So we have these hidden layers, and this is of course just a picture, right? This is not actually, we don't use a what is it, 5431 net, but we use a bit more complex nets here. And I put just one dot here for the features, for the variable truck features, okay? Because that's not all. That's the basis, that's the core, because that is really giving you the information of the state of the truck at every point in time, basically. But we add some more. And so, for example, one thing you can think of is, how about I want to add information about the truck itself, right? And one way of doing that is to say, all right, we give every truck an ID. So it says something like a one-hot encoding or something like that. But, well, there are disadvantages of that. So what we want to do is, I like to think of it as an embedding, basically, right? We take a truck and decompose it into a type of truck, let's say brand, fuel, for example, or tire, or engine size, or whatever, right? Like something like that. And then we have this little neural nets before the actual neural net. And this is kind of an embedding of that truck into one number. And we can do similar things with, for example, the road, right? You can think about the road type. So in Germany, that would be the Autobahn, Bundesstraße, Landstraße, inner city, things like that. You can say something about construction, is there construction site or not? Maybe quality of the surface, maybe something like number of lanes. And again, you kind of embed that into, let's say, one number as an example. And then we get more data here. We get the permanent truck data, road data, weather data, but even driver data if you want, right? We can somehow embed the driver in a number. And then what we rather use, we use something like how many days or years of driving the driver has already, or what type of training, for example, the driver has had. Things like this can all go into this. And then we have a neural net that use all these kinds of features. And then you do I'm sure I don't have to explain this to this audience with backprop and everything. I hope that's clear, but please ask me. If it's not clear, I'm happy to explain.
Yeah, just maybe to understand. So the target value is the fuel consumption per distance, or in order for the whole trip?
Okay, so we train our model on these small little snippets, as I explained, right? Because the trucks, they send the data, let's say every 30 seconds. Mm-hmm. So all of their movements, everything they ever do, is decomposed into snippets of 30 seconds. And, okay. And we get so many of them that it's easiest to train on that value, right? On that fuel consumption within those 30 seconds. And okay. we have the features for those, right? That's truck data, basically. This we call it the variable truck data. And then we have the other, as I explained, they also go in there.
Okay, and somewhere in the features, then I guess, is the distance covered within the snippet or something?
Yes, yes.
Okay.
I hope I had this here too. Oh no, I didn't. It is implicit here, the odometer reading, right? The odometer is like the lifetime distance that the truck ever traveled. Okay. So it's it says 100,000 to 20 whatever, right? And you have you get it now, and you get it in 30 seconds. You take the difference, and you know the distance it has traveled. Similarly, actually, with the fuel consumption, the number that we see is lifetime fuel consumption, and then you take the difference, right?
Okay, understood.
Yeah, and not surprisingly, the distance and the speed are the most important factors for the fuel consumption. Right? The longer you go, the more fuel you consume. The faster you go, the more fuel you consume. Very, very simple. It's not so surprising. But the others also obviously play a role. But like always in these neural nets, it's not so easy to directly pinpoint and put your finger on where is really the feature that is describing this or that in the end. Okay, so the target value is the fuel consumption that we get already basically labeled, right? We don't have to do anything. And the feature vector is the state vector plus maybe, if we have it, these other things like the permanent truck data, road, weather, and drive. This is our model. And it has an advantage over the first setup. First, initially, we trained one model for every truck. Random forest, right? Every truck, and you just train it. The disadvantage here is if you have one model for every truck, is that there's no kind of cross-learning. Whereas if you have one model for all trucks, then a truck that has driven, let's say, only in Germany, can still be run on data that was acquired in Spain, because the model has learned information about the Spanish roads. And this is not possible if you have two different models. If you have a random forest for one truck that's running in Germany and one truck that is running in Spain, and now you let the models run on the respective counter data, it's not so good because that model has never seen that type of data, and then typically the predictions are not as good. If we have one model for all trucks, then we benefit from this cross-learning, but we had to introduce this basically the truck ID here through the permanent truck data, because we have to tell the model somehow which truck are we talking about. That was really something that I say this now in 2 sentences, right? But it took a while until we kind of figured out how we do that, because initially we took the data and ran it through a random forest and had a model for every truck. But it was really worth the effort, because we have not only this one advantage of somehow cross-learning, but we have another advantage as well. We can answer these business questions now very easily. I think this is really a neat thing. One thing that we first need to understand, though, is a problem that we also faced was, okay, let's look at these that I highlighted here, the speed or the gear, right? If I really want to, I'm sorry, I'm going back again. I explained to you analysis, looking in the past, and prescriptive looking in the future. Now, if we want to look into the future, our problem is that some of these features we don't know in the future. Right, the odometer reading, okay, we understand that because it's really the distance, that's good. But the speed, well, what's the speed? If I ask you tomorrow, we're going from Berlin to Munich. And also the gear, let's say, right? So how do we do that really? And here, yeah, sure.
Before discussing this question, may I ask a question from the chat?
Yeah, right.
There we have, where do you get your weather data from? Is it measured by the truck, or do you use an API?
Yes, I wanted to talk about this actually. Yes, no, the truck sometimes has a temperature reading, but no more than that. No, we get weather from, in Germany, it's called Deutscher Wetterdienst, DWD, and we are also collaborating with a company that helps us actually put that in a, for us, better consumable format. And the good thing about this weather here is that actually that you can predict, right? And people actually do that. So they are able to, yeah, this is, I mean, really, if you want to predict how your truck is driving tomorrow, and you have trained on weather data from yesterday, then you also need to give your model data of tomorrow's weather. If you don't, then the model doesn't work. And so we are working for the weather. We're working with this company, and we get basically data from Deutsche Wetterdienst. For speed, we found a service is called Here. It's basically more or less a routing tool, but it also gives speed, and that is interesting for us. We were also thinking about predicting ourselves. But if you get that kind of data, it's obviously it's easier, right? Yeah, and this is how we do it then. We use that to then really predict in the future. The model is the same, right? We didn't change anything in the model, just making sure that we have all the data even for future trips. And then this is what we can do, right? We can look at different trucks, we look at different drivers, and we look at different tours that they drove yesterday. We can make our analysis for each one of those. And in looking in the future, we can also look at different trucks and different drivers, and maybe, let's say, different routes, right? Going from Berlin to Munich, you want to go this way or that way or the third way, right? It's just something that we can simulate if we want, right? It's already there, basically, as soon as we have our model trained and everything in place. So there's I wrote here at the top of the slide, there's an arsenal of simulations that we can do, right? I mean, this is only 3 by 3 by 3 example, but obviously we can we can scale this up, and that's scaling exponentially. All right. So with these things, now we can start answering real business questions. And these business questions, they usually translate into saving fuel, because that's what the fleet owners are really interested in. They're maybe not so interested in saving CO2. They're interested in saving fuel, but that obviously translates into saving CO2. So we started with how efficient was I, right? And I explained that, and I think it's clear to you, but we can ask other questions. So how much could I have saved? That's the next question they ask, right? If I say you were efficient or not, the next question they ask, and how much could I have saved? Well, we go back to this picture. How much can I save? Very simple, this much, right? You drove from Berlin to Munich yesterday. We do all the simulation with, let's say, 1,000 trucks. We find 200 trucks are better than you, and they consumed 2 liters less than you, or 20 liters, or whatever, right? That is an answer. It's a valid answer. It's very sound. I mean, we can repeat this. It's very robust, I believe. And one thing that maybe a little side remark, right? A topic that is very present in the AI community is explainable AI, right? And no, our AI doesn't explain that. It's our natural intelligence that explains that. It's us, right? It's the people that look at the data and then explain something. And here we can explain how much can you save.
Can I ask a question there?
Yeah, sure, go ahead.
Stop me if you're going to explain this later, but I mean, okay, you could have saved that much, for example, by switching the truck, but then you would have, let's say you have an efficient and an inefficient truck, but you still have to use both, right? So not all of the potential is realizable without exchanging the hardware, I guess.
Mm-hmm. Yes. A few remarks here. Number one is we let also trucks run on your trip that you don't even own. So it's not even an option for you to exchange that truck, right? Let's say you only have MAN trucks. Mm-hmm. And we also use DAF trucks on your trip, and we will tell you, okay, all the DAF trucks. And that's actually something that's going into the next slide. The next question, like, how can I save, right? Okay,
then you're going to explain it.
No, but it's still very valid. It has a different aspect to it. This. Let me explain this first, and I come back still to the other aspect. So how can I save? Well, what we do is we look at all the trucks that perform well, and let's say they are all DAF trucks. Even if you have an MAN truck, it's still a valid information for you, right? Mm-hmm. I mean, you rather have this information than not. But there's also other things that we can look at. We say the tire pressure is half a bar higher than yours. Or they have a spoiler, right? Or I don't know what, right? Anything can happen. And what we really do is we look at these trucks that perform well. And also it goes on both sides. What should I avoid? Right? Let's look at the trucks that are doing really bad here. Right? So then then we look at those trucks and we say, well, and please don't buy a BMW truck, or I don't know, you know, something like this, or don't use a spoiler. That's really hurting you, apparently, even though you don't have a spoiler, right? But we tell you, well, see, the trucks that are doing bad on your trip, they all have a spoiler, so don't even think about it, maybe, right? But the other thing that you said was more, let's say you have two trucks, right? And I can tell you, well, you should have used the other truck, but then the first truck must have gone on the other route because they were both driving, right? We can still simulate that as well, right? And I think it's even in the, yes, it's called the optimization, or what is the best dispatch, right? That's the question here. Yes. And what we do then is we just vary the truck basically and the driver, if you want, on all tours. So my example is usually you have a north route and a south route tomorrow. You have a red truck and a blue truck, and you have Alice and Bob. Right now, you have all the possible combinations, and of course, we know that Alice cannot go both on the north trip and the south trip at the same time. That's not possible, but we can still find the best combination. Right? This is still possible to do that. And that doesn't necessarily mean that the best truck goes always on the best tour. It's just, I assume you speak German, right? And you know, I'm a football fan, so there was this famous coach who said, nicht die besten 11, sondern die beste 11 gewinnt, right? It's the team, it's not the individual players. You don't need to look at every individual tour, but it's really the combination that makes it, makes the best consumption. And this is, yeah?
Sorry, can I reingrätschen?
Yeah, please, as we're talking about football, of course.
I was wondering if your model is also able to consider actually what is delivered, like basically what is in the truck there, because as you said, you may have a choice of trucks, but you may also have a choice how to distribute the goods you are shipping. Is that also somehow implemented?
No, not the type. What we do use is the weight. That is obviously makes an impact, but not the type. For this example of the the north route and the south route and red and blue truck and Alice and Bob, obviously you do have to take into account that not every truck can carry every kind of cargo. Here we rely on our customers, right? They have to tell us, let's say this is hazardous material and can only be transported by truck A and B. Or this is liquid, it only goes with truck C and D. And in reality, there's always more constraints to it than, just any combination is possible. So we have to have kind of a pre-optimization, or no, it's a constraints, right? Boundary conditions, I would call that. That our customers tell us already. Yeah.
But technically speaking, you could get more than weight, right? You could definitely find out if it's a gas or liquid or solid, right? From the way the truck moves, like with the braking and everything, you should see a pattern there, shouldn't you?
So we have never looked into that. We haven't thought about this, and I would be a bit skeptical because. So
I know for liquid for sure, because liquid has a different way for the brakes than for solid. I don't know how is it with gas exactly, but for liquid, and they actually have to brake differently a truck than if it has a solid container.
I believe that, or I understand that, but our data is not. You see, we get snapshots, right? We get the state right now. And then 30 seconds later, we don't see how do you brake over a period of 30 seconds. You see what I mean?
Okay, I understood. I was just wondering if you would combine it, you would do it, but that's not what you're aiming for, so you don't.
No. Also, I mean, this type of information is something our customers are willing to give us as well, right? We don't need to extract it from the data, whether it's gas or liquid or solid, as an example, right? This is. Our customers know what they are transporting.
You agree? I just thought, for instance, what if you have loose cargo, right? and this would make a difference then. And obviously you could see that in the data, but your customer doesn't tell you it's loose, but you actually can say, oh, well, hang on a second.
Yeah, okay, I understand. I mean, it sounds like an interesting topic also to explore. But what we would really need is then a long period of recording of the sensors, right? And not the snapshots. I believe the snapshots are too sparse.
Yeah, probably you're right. I mean, this is, but I just opened up maybe new use case for you.
Yes, no, I understand. It sounds interesting. It sounds interesting. We don't have access to that type of data. That data is in principle there because it's, you know, the sensors are in the trucks. It is probably not recorded because you have to see it costs money to send that data to the cloud while they're driving, right? This is done through SIM cards, and so you kind of pay for the volume that you're sending in the cloud. And if you want to continuously record all the sensors, it's probably expensive. You could maybe record it on board and read it out at the end of the day, which is okay, basically, for us, right? We don't need to have this really in real time. But currently, I don't know. The companies that provide this telematic data, they don't make this available to us. I can tell you that, right? They make only these snapshots available to us, but not this continuous reading of the sensors.
Understood.
Yeah. But yeah, well, thanks for, you know, good thinking. That it's definitely something that that I agree. We should be able to see if we have the data here. Yeah, I'm almost done here. What I really want to say is what I like here is that we are looking at business problems, and we start with the business question. And only then we go and you know, do all the ML and all the neat thing and optimize the operations. And when I think about this, it reminds me of my time as when I was a kid in elementary school, and I believe, yeah, there's something very similar. Maybe you remember when you had math exercises, they sometimes read something like this. You have 15 apples and you have 2 friends, right? And then the question is, how many apples does everybody get? And then for the elementary school kids, they first have to figure out, well, I am one of them, so it's 2 plus 1, we are 3. And then 15 divided by 3, you get 5. And then if I do that, and I was all happy, right? And I wanted to move on because I wanted to be fast, then I would never get full score. They will always say, hey, you forgot the answer question, the answer sentence, because I have to write, you know, everybody gets 5 apples. And this situation reminds me very much of what we're doing here at Trax, is you get kind of a text, right? Something like saying, okay, what's efficiency or something like that. And you have to analyze it and understand it. You translate it into a formal language, you know, you solve it with AI, just like the elementary school kids, they solve it with 15 divided by 3 equals to 5. And then you're not done. You have to translate it back. You have to formulate a sentence at the end, right? I have to tell them something about what I showed you, these distributions, and we formulate we call it the green index, and say, okay, you're at 80%, and we have to explain what that means. We cannot just say you're at 80%, but we have to explain these things to our customers. So it always reminds me of that situation, of these Textaufgabe, it was called in my school. And I think this is really at the core of what data scientists do. They take somehow real life problems, need to understand them, analyze them, translate them into a formal language, solve them there, and translate back. That is very important. Translate back and make it understandable for the customer, and then actionable, obviously. And yeah, I hope I was able to show you a bit what we're doing here. I have 3 messages that I like to present you, or maybe also some challenges.
Can I have, before you do, you might have another question. So I mean, I understand your company selling point to us at least is reducing CO2, but I feel underlying here, there's still this idea to the client to say you also save money, or you know can increase your revenue. So now wondering, I mean, there are ways of optimizing your model. Do you actually more optimize towards saving money, or you actually optimize the CO2, or do they actually go in line just by coincidence?
I say the model is optimized to neither. The model is optimized to accurately predict the fuel consumption. Okay, and the fuel consumption we get from the data that they collect. It's just there, right? It's not positive, negative. It's not money. It's just the fuel that has been consumed. And the question of whether you reduce CO2 or fuel, that is really a question of our customers then, right? It's we give them actionable insights, and they have to do whatever they feel is best for them. In reality, the CO2 emissions and the fuel, they go hand in hand, right? They can, if they reduce fuel consumption, they will also reduce CO2 emissions. There's some things, of course, that they can do. They can change the fuel. They can use, for example, biodiesel or LNGs or others, and that will change the CO2 emission. But let's say you are with one type of fuel, then reducing that fuel will also reduce the CO2 emissions. That is aligned. Was I able to answer your question?
Yeah, okay, answered, thanks.
Okay, cool. All right, 3 messages that I usually like to tell the people, and hope to maybe also spark a bit of a discussion. I believe natural intelligence is more important than artificial intelligence, and it's something that I said at one of the slides, where I say, see, we get the insight through the natural intelligence by, us people looking at data and interpreting it. And the artificial intelligence is helping us, of course, right? It gives us the data, but it's actually, in the end, it's the natural intelligence. The second one is science before data. We are thinking about these things a lot before we do something, and we look at the data that we have available and that is probably impacting it or not. And the third message is whiteboard before keyboard. I like to be at the whiteboard quite a lot and talk with my colleagues about it before I go to the keyboard and start coding. Yeah, those are 3 statements from me, personal opinions. I'm happy to discuss if you agree or disagree. That's also interesting. And with this, I'm done. Thank you very much for your attention. If you're interested, please contact me also on LinkedIn. My email address is here. Or now, of course, any questions and discussions are very welcome. Thank you.
Thank you.
Thank you, Daniel. Very interesting talk. So we have a few minutes left. If there are questions right away, please go ahead.
So I have a question, but it's more philosophical. You said
those are the best.
You said science over data. Isn't that a bit contradictory to the new data-centric approach promoted, where data science should head? Oh, what's your take on it?
Yes, I see. Yes, so to contradict myself, I can say no. AI is about having large data sets, not putting any brains in there, but just throwing it at some models. Of course, making sure that the models are good and having good labels and stuff like that. And then whatever comes out tells you something. That is kind of contradicting myself now. Maybe what I want to say here, science is be scientific, be accurate, be question yourself. Don't trust good results. Rather think it's a bug. before celebrating that you are going to win the Nobel Prize. Things like this.
I think maybe what I'm getting out of what you're saying is be skeptical about your data. Don't take it as face value. Is that maybe what's the idea? Okay.
Yes. Also.
Well, then I think it was still in line with being data-centric, right? You just be careful what you're looking at.
I think, I mean, take all three together: natural, science, and whiteboard before artificial data and keyboard, right? And I'm not saying don't do artificial intelligence, don't go to the keyboard, don't use data. I'm saying, you know, there's an order, and you should first think, be scientific, and write it down on the whiteboard, and only then you go to artificial intelligence, the data, and the keyboard. Maybe that's a better way of putting it.
Understood.
I think I agree. Though
Okay.
sometimes you are under time and effort constraints and just have to analyze the data and hope for the best. I have another remark. It's also more academic, but what you're doing in the descriptive, not in the descriptive, but the predictive part, I think it could be viewed as causal inference, because you are actually playing like, what if we changed a certain input parameter, right? And keeping everything else kind of fixed in order to say, okay, if your truck had a spoiler, X would have happened, right? And the difference between the causal inference and the prediction is that maybe all trucks that have a spoiler are more efficient, but maybe the reason is because they have a different type of engine, right? So you have these types of correlations that don't necessarily mean that there's a causation. And I'm maybe curious how you deal with that, because in order to deal with that with the causal inference framework, you would need more than one input layer, right? You need to structure the inputs as well. But I'm certain you have thought about this, right?
Yeah, well, I think this is a good example where, see, the natural intelligence goes before artificial intelligence. I fully agree with what you said, right? And that's why we don't do that. We don't go and just put the spoiler there. That's not how we do it. The only thing that we vary is a whole truck and a whole driver. Okay? So it's really the idea of letting a different truck go on the same trip, but this different truck exists, right? We don't put it together as we please. It's actually.
Sorry to interrupt, but if you say that, okay, what do all the good trucks have in common?
Yeah.
And you are kind of averaging over several trucks, and the resulting property doesn't necessarily exist, right? But a resulting average.
Yes. Okay. Yes. But let me make it still very clear, the distinction, right? We don't go into our feature vector and change from, let's say, that one feature from not spoiler to spoiler, right? For your particular truck. That's not how we do it, because then I would think, yeah, that's probably not helping us. What we do is we take the truck, the whole truck, so we change all the features to resemble a truck that actually exists and whose data we actually have and has actually driven, right? And then we take 1,000 trucks, and all these 1,000 trucks we do and run on the data. And then my example was to say, okay, let's assume in these 1,000 trucks, right? Let's assume 200 are better than your truck. And just to be extreme here, all of these 200 trucks have a spoiler and are and don't share anything else, right? They have all different type of brands and all different kinds of engines and so on. And we look at the bad end of the curve, and we see they all don't have a spoiler and don't share anything else in common. But and this is you see now, this is natural intelligence, right? We're looking at the data, and of course I made something up now. I made like a perfect example, right? But yes, this is how we then analyze it. Of course, we look at the data and say, okay, how of the good trucks do we find common features, basically? And feature, I don't mean now in the sense of feature vector, but as a spoiler, or do they all have a particular kind of engine, or I don't know, whatever you can think of. This is really how we go into that, and the causality. Yes, that's always I mean, the only thing we really know is correlation, right? Causality is always something that that we, the people, the natural intelligence, puts in, and I think you have to be careful there and have to really. I mean, you pointed out very well, right? You cannot just blindly do that and say, oh, now it's the spoiler. No, you have to be very careful about that. I agree.
But I understand that in the optimization phase, where you only recommend existing combinations of features because you recommend a specific truck, there the danger is much more mitigated, right? There it could only be things like, I don't know, you have two drivers, Alice and Bob, and Alice is like the best fuel saving driver ever, and so far has always driven truck A, right? And Bob, the wasteful guy, always drives truck B. Then you might run into the same problem because you are again recombining features.
Yes.
But it's less likely than if you say, okay, please just saw off the spoiler of your trucks.
Yes. Especially, I agree with you, especially with the drivers. I think that is a very shaky ground, right? As you point out, right? Alice always drives the blue truck and Bob always the red truck. And so maybe it's not Alice that is good, it's the truck or that particular combination. Or yes, that is in particular tricky, I believe, yes. That's why my examples are more on really features of the truck, like the spoiler, right? Or the tire pressure. Tire pressure and spoiler are also, I mean, when you look at causality, it is something that we would easily see a causality with a spoiler and a tire pressure, right? That fits into our physical picture, definitely. Whereas if the correlation was, in fact, the color, right, blue or red, then we would say, we'd be very suspicious.
True.
Yeah, but yes, I agree with you. It's shaky grounds. It's not so easy to say if you change that, it will really happen, right? It will really optimize things. It's not so easy all the time. But what we can do is we can firstly run a prediction for, let's say, 2 trips tomorrow, right? And now the dispatch makes a decision, whatever it is, and then they run. And then after they actually run on their trips, we can do the analysis, the backward analysis, and compare our backward analysis not only with reality, but also with our forward prediction 2 days earlier, right? And the more everything is in line, from more angles you look at, and if they're all in line, the more confident you are that you're doing something sensible here. Yeah,
I agree.
Cool.
And one question, sorry, I joined late. So based on the discussion that we are having right now, so like to assess these kinds of systems, like you mentioned, how are we doing like forward prediction and then going back and looking at the like recommendations that we're giving and how good are these recommendations working in real life. So how much time do you think will it take to really come up with like an accuracy metric or some kind of metric to tell the system is really working good?
So I'm going to say, so the computational time is not a problem, I think.
Yeah.
Okay. I mean, just from computational cost, it's not a big deal. The problem is more the adoption in the industry. When you think about this, this industry is rather run by hands-on, blue-collar kind of guys that are not on the, AI is not in their everyday life. They are rather skeptical about these things. So the question is more, how long does it take us to convince them to actually do something that we suggest? That is, I think, the most time-consuming part. We are working on this already for a while, and we have a few customers whose data we have, but they're not even thinking about us telling them the dispatch. What they think about is they want to tell us the rules by which they dispatch, and we should write a program that makes the rules as they tell us, right? It's yeah, they say we have two guys that do it always this way. Can't you write a program that does it this way, the dispatching? And we say, yeah, well, you know, they're thinking about different things. It's yeah, maybe a bit too early for them, but still, what we can do is we can just run predictions, even after the fact, right? We train the model only with data that was available before the trip, and then predict the trip that we know has happened, and then compare with models after the trip, and so on and so forth. So, I mean, we can run back in time any way we want, and this looks good to us. We find this convincing. We believe that we can still do a bit more with extra data. Especially after weather, especially we feel like road is an interesting, mostly the surface can improve, we believe. And then, yeah, in the end, you never know, right? Because I predict that tomorrow from Berlin to Munich, it's gonna consume 100 liters, and then there's a traffic jam. And then then you're off, of course, then you're totally wrong, right? It's hard to predict things, especially the future. Yeah, but yeah, I agree with you. It's an important question, like how good are we, and how long do we need to actually optimize it to such a point that we're able to do that regularly, right, in the production, basically.
All right. Thanks, Daniel. Thanks, Pranay, for this question, which was unfortunately the last question, because checking the time, we are already a few minutes past 5. Daniel, thank you again very much. I liked really much that this topic tackles both sides. So the specific application and the use case and the added value for society. And as you mentioned, it's then not the model or this specific algorithm that makes the difference, but like you can add a algorithm that suits your needs. You can choose a neural network decision tree as you like. But I really like that you emphasize that it's not the algorithm that is in the focus, but really the application and the business case. So let me thank you again. Big virtual applause.
Thank you. Yeah, it was fun. Thank you. Thank you for the questions. That was also, it's always very rewarding to see that you have an engaged audience. Thanks a lot.
All right. So we're going to put this on YouTube. The slides will be available, I hope, on our Discord channel. Please check out the meetup for next Tuesday. And having said that, have a good week. Be productive, be brave, and master the complexity.
All right. Thank you. Bye-bye.
Thanks, everybody. Bye.
Thank you. Bye.